Hello everyone. In this video we will perform analysis of a plate with a hole and is subjected to the load. So consider there is a plate whose one face is fixed and there is a hole inside a plate at a center, and the hole is subjected to a load of 10,000 Newton. So the dimensions which we are using is 100 by 100 mm plate with a 5 mm thickness. The hole is of 25 mm diameter. So here we are using a material properties as a steel whose Young modulus is 210 gigapascal. Uh, Poisson ratio is 0.3. Yield strength is 240 megapascal and factor of safety is 1.3. So first of all, from the factor of safety we know that factor of safety is defined as the ratio of yield strength upon maximum allowable stress. So the allowable strength is defined as the ratio of yield strength upon factor of safety. So the value of yield strength is 240 megapascal and the factor of safety is 1.3. So based on that, the value we obtained is 184.6, right? So 184.6. So this is the maximum allowable value that the material can withstand. If the value of stress is higher than this, then material will fail, right? So for this plate we will perform the analysis in ANSYS, and then we will find the maximum and minimum stress acting on it, and based on that we will compare the result. We will compare with this value and then we will conclude the whole problem. So in order to perform the analysis, first we will go to workbench. So in the workbench, go to static structure. First select the unit. Here we are using metric unit. So the first step is to define the material properties. Then in the engineering data, then we will create a model in geometry, and then we will apply the boundary conditions and loading conditions and generate a solution in model. So let's go to our first step, that is engineering data. Double click on it. So the material that we are using is steel. So this is a predefined material. So let's define a new material, that is steel. So here the material is linear elastic, that is it is directly proportional to stress, directly proportional to the strain, and it varies linearly, and it is elastic, means on deform it will get again return back to its original position. So here for this the properties that we are using is isotropic elasticity. So click this property and drag it on our new defined property. So these are the this yellow bar means these are the required properties. So the Young modulus is 210 gigapascal. So first we will set its unit as megapascal. Then we will write 210000 megapascal. Poisson ratio is 0.3. Press enter, and based on that we will the bulk modulus and shear modulus is automatically calculated. So our first step is completed. Now our second step is to create a model. So right click on a geometry, go to design modeler. Here you can use space claim and discovery also. For this problem I am using new design modeler geometry. So the first step of this is to select the unit. So here I am using a millimeter units for this problem. So I am selecting this millimeter. Now select this plane, go to sketching. This is the plate. So first we will draw a rectangle and then we will create a hole and then we will extrude it with a depth of 5 mm, right? So select the rectangle, select the plane, then draw the rectangle. Inside the rectangle there is a circle, so I am drawing the circle. Now I have to set the dimensions of this rectangle and a square. So go to the dimensions. This vertical side is V1. Click on this horizontal side is H2. Click on this circle, that is D3. Now set D3 value is 25, that is the diameter of hole. H2 means side of the plate is 100 mm. V1 means vertical side of the plate is also V1. Here the circle is not at a center, so in order to set it as center, we will set this value as a 50, and this value as 50 is to move this circle to a center. So this L4 is set as 50 mm, and this L5 we will set it as 50 mm. And here you can see the circle is at center, right, of the plate. In order to rotate this sketch, use the scroll button of your mouse to rotate this sketch. In order to move it, you can press Ctrl along with Alt and scroll to move the sketch like this. Right, now we will extrude this part, right? So go to modeling, in our experiment click on sketch and then click on extrude, right? So here, apply it. Now here the dimension, depth for which we are, our depth of the plate is 5 mm, right? So we will extrude it up to 5 mm and then we will generate it. So here you can see the our model is created in 3 dimensions along with depth. Another thing which you can change is, if you want to draw create a on symmetric, you can also create a symmetric part also. Like if we select both symmetric, then it will create a both 5 mm thickness on both the side of the plate. Like here there is only one side of plate, right? But if you select both symmetric, then it will create uh, geometry on both side of the plate, as you can see here. But I want it on one side only, so I am again converting it back to normal. Click on generate. So this is our model. Now we'll perform analysis. So close design modeler. So our third step is to create a meshing. Apply a material on the model, create a meshing, and then apply the loading and boundary conditions, and then generate a solution. So for that we have to go to the model, right click and edit. So this is our model. So this is the place where we will apply the material on this model. Then we will create a meshing, and then we will apply the boundary conditions and loading conditions on it, and then generate a results, right? So first let's apply the material. So click on geometry, solid. Here in assignment there is a structure still. Change it to the steel property that we have defined. And now then go to the mesh. So this element size is default, so let's generate a default mesh size. So right click on a mesh and then generate mesh. So the mesh has been generated. So as you can see, this is not a proper mesh. As you can see, there are distortions near the circles, so we can easily improve it by changing its mesh size. So this we can change it by setting this element size, but first we have to set a dimension. So in unit, go to mm, select a metric part, and then go to the element sizing default. Let's say I am setting a 3 of element size, right, for meshing. Then right click on mesh, update the mesh. As you can see, mesh has been created, and you can see the meshing has been improved on near the circle side, right? The distortion is less as compared to the previous one. You can also check it by reducing the element. So let's say I am reducing it to 2.5, and let's see whether the mesh generation is good or not. As you can see, the mesh is little bit better than the previous version. So there are various properties which you can alter in order to obtain a fine meshing, which we can discuss in earlier in later video. So there are various properties which you can change, and based on that uh, there are changing in mesh size and all those things. So general, we are keeping it as a general, that is 2.5 mm for this model. Now our next step is to apply the loading, boundary conditions and loading. So first we will apply the boundary condition. So click on static structural, right click on it, insert, and then fix support. So as you can see, we are applying fix support on one face and then loading on the edge of the hole. So we are applying the fix support on one edge of plate. So I am applying here on, I am applying on this face, right? So select this face, click it, and then apply it. So as you can see, the fixed support has been applied. Now I will apply the load. So right click on static structure, insert, and you can select force from here, right? There are other loading conditions also, like bearing load, moment, other boundary conditions also, like fixed support, displacement support. Based on your requirement you can select this. So our requirement for this model is force. So click on force. Here I am applying in terms of components. So I click on component. So in component there are x, y, and z components. So you can apply the load based on these directions. So here we are applying the load in down direction, that is negative of z. So the value is 10,000 in down direction, right? So I will select 10,000 and in negative, so that it will apply downward, that is on opposite side, in on negative z axis, right? Then we will select at edge on which the load is applying. So the load we have to apply it on the edge of the hole, right? So click on this geometry selection, click on this edge and zoom it. Now I am applying the load on this edge. So click on this and then apply it. So as you can see, the load of 10,000 Newton is applied in down direction on the hole. So our load boundary condition of fixed support and our loading condition of applying the load on the edge of the hole is applied. Now I am performing the solution. Now I will solve it. So the output which we are required is uh, deformation. So go to the right click on solution, go to the insert, go to the deformation and click on total. Also we have to check the maximum stress acting on a plate. So right click on solution, go to the insert, go to the stress and click on equivalent 1 misses. Then click on solve. So as you can see, our results has been generated. So click on the deformation, and if I will play this graph, then you can see that based on the load it will bend in downward direction. This is the fixed support. In order to, you can increase the scale by from 1.5 to 7.5 to see the exact deformation in larger scale. As you can see, the plate is getting deformed in downward direction. So the maximum deformation is 4.74 mm and the minimum deformation is 0, right? So now we will analyze the equivalent stress. So click on this equivalent stress and you can see the maximum value, that is 1261.4 and the minimum is zero point 0.4. So go to the results. This red part is a portion where the maximum stresses are acting, and this blue part is a portion where the minimum stress are acting. You can select maximum part and it will show the position where the maximum stress is acting. So as you can see, this is a point where the maximum stress is acting. For minimum, this is a point, and if you want to check the stress on the other position, then you can select on probe. So based on this, if you want to find a stress on this part, then you can obtain it by clicking it on here. If you want to select this position, then it will show this stress. If you want to select this position, it will show this stress, right? So the maximum stress is 1261, and this is animation. uh, so the maximum stress is 1261.4, which is much higher than 184.6. So the material will fail easily. So if you want to improve the strength of the material, then material or a tool sorry material or a plate, then you can easily change the dimension of the tool. Like let's say if you can increase the dimension thickness of the plate, then maybe there are chances that it will fail with less stress. So you can also do this analysis at home by changing its dimension and check whether that how much stress is acting on a plate by changing its dimensions. Thank you.